Hi, it's time for another math easy solution to discuss further into conic sections and now look at ellipses, and in this video I'll go over the definition and derivation of the formula for an ellipse, and this also includes circles. Circle is basically a type of ellipse. So yeah, let's just go and dive right in. So conic sections, ellipses, but first I want to make a note. I had made a previous video on the definition of ellipses, but I'm revisiting it to better tie them to the conic section series that I'm making right now. So yeah, you may have seen my earlier video. I think it was a couple of years ago I went over ellipses back then, but I'm just revisiting it now because it's going to be part of this conic section series. So now recall that parabolas, ellipses, and hyperbolas are called conic sections because they result from intersecting a cone with the plane as shown below. In my earlier videos I went over the parabola where you cut through a cone like this and then you get this parabola. Now if you cut through one of the cones you get an ellipse. If you cut through both sides like that you get an ellipse like that, and if this is perfectly horizontal what you end up getting is a circle. That's everything is symmetric like that. And here you get a hyperbola if you cut vertically on this cone section, this mirrored cone like that, which is basically two parabolas, one up, one down, etc. So let's jump into ellipses. So the definition of ellipse is over here. So an ellipse is the set of points in a plane, the sum of whose distances from two fixed points Fi and F2 is a constant, and this is as shown below, which I'll draw right now. So this is the definition of an ellipse. So if you had, let's say, 2 points here, I'll call this F1, then we had another point here, I'll call this F2, and now let's say we had a point P right here. So now from here to here we have a distance like that, and then here to here we have another distance. And I'll call this point right here P. Yeah, so basically this ellipse is the definition is the sum of the distances to any point on this curve is going to be constant. So for example, F1 and F2, so P, F1, if you add these up, the distances, yeah, plus, move that over, so plus P, F2, so the distance from here to here is going to be constant like that, and that's basically the definition of an ellipse. So if the point was somewhere, let's say you had the point over here, then what we end up having is, well, this dashed line, it's going to be something like this, so it needs to be evened out. So if this line is longer, then this one needs to be shorter like that, so we get something like that. And if you keep doing this, what we end up getting is just a shape that looks like our typical ellipse shape all the way around. And here I'll draw this another color. So let's say from here to here it's going to be all the exact same distances. If this point was a P in red, different point like that, it's all going to be constant. Yes, alright, so I just moved that over here just to make it look better. So now these two fixed points, the F1 and F2, these are called the foci, which is just plural of focus, like that of the ellipse. So one of Kepler's laws is that the orbits of the planets in the solar system are ellipses with the sun at one focus. That's interesting point there. Now if you go to Wikipedia, just a quick mainstream view of this of Kepler. So Johannes Kepler, or Johannes Kepler, he was a German mathematician, astronomer, and astrologer. So he was born in the 1957 to 1630, and he was a key figure in the 17th century scientific revolution. He is best known for his laws of planetary motion based on his works Astronomia Nova, Harmonices Mundi, and Epitome of Copernican Astronomy. These works also provided one of the foundations for Isaac Newton's theory of universal gravitation. So yeah, just an interesting brief history lesson on Johannes Kepler. So let's go further. So in order to obtain the simplest equation for an ellipse, we place the foci, so those 2 points, on the x-axis at points -c and c, as in the figure. Yeah, so that the origin is halfway between the foci. Yeah, so what I'll do right here, draw the y and x axis like this. So let's say we had a point here, we'll call this one, this is the F1, and this is at negative c and 0. Yeah, actually I'm going to move it a bit more to the left like there, and this is the origin 0, and now we have it just to make it symmetric about here. So now at this point we have, this is f2, and this is at c 0 like that. So yeah, now that we have this right here, let's just draw our ellipse. So it's going to look something like this, that curve, and then we get it around there. Now let's say we had a point over here, we'll call this P, and this is at x, y. So now the distance from here to here is that. Then we get a triangle that looks like this across to here. Yeah, so now we have this triangle like that, and we can determine the lengths of these two line segments by, well, just splitting this up into two triangles, like that, as a right angle like that. Now the height of this triangle is going to be y, that's just a point y there, and at this point here we have x, so at this point is x, so in other words this length is x, and now this length is just c, and then this length between here, this is just, well, the difference, because this is from here to the origin is c, so this is just c minus x, or just if we look at an absolute form, and I'm going to switch it around, this is the same thing as writing x minus c, the absolute. This is assuming c is greater than x there, and we're going to be squaring it when we find a distance, just using Pythagoras right there. And now what I'm going to do is I'm going to let the sum of the distances from, fix that spelling, so from a point on the ellipse P to the foci be 2a, and which is that constant, and this is just greater than 0, and then P of xy is a point on the ellipse when, so it's on that point when we have the distance from f1 to p and f2 to p there. And what I'll do is write p f1 equals, the absolute value of it, the distance pf1 plus the distance from p to f2. This equals to, well, 2a, and that's what we're setting it to, and this is just a constant that's written as 2a in that form. And then here, if we just apply Pythagoras, we get this distance is going to be, now we have a triangle where the sides, the height is y, and the side here is x plus c. So now we have pf1 as x plus c squared plus y squared. Now we have to add this triangle's length here, again using Pythagoras. This is just going to be x minus c, the absolute value, x minus c squared plus y squared, and this one is the same thing as equaling to, well, x minus c in normal brackets like that, not absolute value, because it's going to be positive regardless. And now this equals 2, and this is a squared there, this equals to 2a. And I'll just write this as by Pythagoras, or Pythagorean theorem like that, and you can learn more about that in my earlier video where I prove it. So now what I'm going to do on this this case, I'm going to move this one, which is as the positive x plus c, onto this side and then square both sides so we can get rid of this square root initially. So what we'll have is we're going to have square root x minus c squared plus y squared on the left side here. Now we moved everything on the other side, 2a minus square root x plus c squared plus y squared like that. And now what I'll do is square both sides like that so that we're not changing anything. Just do that so we get rid of this square root sign. So when we square root and then we have a square, those just cancel, so we're left with x minus c squared plus y squared equals to, well, equals to this part. We're going to expand this using the FOIL method, so 2a times 2a is going to be 4a squared, and then minus 2a times this big square root. We're going to have, well, 2a square root x plus c squared plus y squared, and then we're going to multiply the square root by 2a over there, which is the same thing as over here, so we can just add those or subtract both because it's negative. So negative 4a like that, and then we can, this multiplied by itself is going to be positive, negative times negative is positive, and then the square root cancels, so we're going to be left with x plus c squared plus y squared like that. And now we can start simplifying what we can, which is this y squared can cancel with that right there, And then we can expand this one, FOIL that out. It's going to be equal to x squared, x times x squared, minus x times negative c, then negative c times x. So it's just going to be two times of the same thing. So we're going to have c, negative 2cx, then negative c times itself plus c squared. Now this equals to 4a squared minus 4a like this, and then we have this part as well. Yeah, this big square root x plus c squared plus y squared like that. And then we can expand this one there. That's going to be, it's going to be here. That's going to be plus x squared, x times x, and x times c, then c times x. That's going to be plus 2 cx, and then c times c is just plus c squared like that. So notice what we have here. Yeah, we can begin simplifying. Well, there's an x squared there, and there's an x, I'll write this a bit softer, so an x squared over there, so we can cancel those, and there's also a c squared. So yeah, we're just trying to simplify further and further, and there's a c squared there we can cancel. And now what we have here is a 2cx and a negative 2cx, so we can move this onto the other side, and then we'll have negative 4cx, so those add up, and then in the negative side. So negative 4cx equals to 4a squared minus 4a, and then we have a big square root x plus c squared plus y squared, like that here. So now what I'm going to do is, well, we can cancel the 4's out. Those are 4's on every single term. And now I'm going to do is move this onto the other side, and then move this thing onto this side, so we get rid of those negatives. So we get a square root x plus c squared plus y squared like that. Now this equals 2. Now we have this a squared. Yeah, now this negative becomes a positive on this side, plus cx, like, and now we can get rid of this square root by squaring both sides again, like this. So what we end up getting is on this left side here, this a is going to be, well, a squared. Now here those cancel. This is going to be, yeah, times it by, the square root just gone now, x plus c squared plus y squared equals 2, and now we can expand this out using the FOIL method. A squared times itself, a to the power of 4, and now we have here plus a squared times cx, and cx times a squared. Well, let's have a 2 a squared cx like that, and then cx times itself is just going to be c squared x squared like that. Yeah, so now what I'll do is I'll just FOIL this out. So this is going to be, well, a squared, and then we have this FOILs out to x squared, x times x, and then plus x times c, then c times x, it's 2cx, and then c times c, plus c squared, and then we have a y squared there, like this. Now this equals, so just write this other side, a 4 plus 2a squared cx plus c squared x squared. Now when you multiply this inside, we get an a squared x squared plus 2a squared cx plus a squared c squared plus a squared y squared. And notice what we have. There's nothing that's a power of 4. We only have power of 2 is the highest here, and also we have a 2a squared cx, and there's a 2a squared cx. And also there's an a squared x squared, so that we can factor out with this c squared and x squared. And then there's also this a squared c squared. So we can combine it if this one was written as a squared, so that we could factor out one of these. And I'll show you how this will work out perfectly fine, because it just gets rid of that squared, power of 4. Make this a squared, so we could do some factoring later on. So I'll just write this down, the rest of this, 2a squared cx plus c squared x squared like that. So now what we have is, well, this cancels with this. Yeah, so that part cancels, and now we have this a squared x squared, and there's a c squared x squared, and we can move that over to the other side and then factor. I'll just move this over to all the way across to the other side, and then basically this is gone. We can move this onto this side and factor out later, do a better arrow across there like that. So what we'll get is, well, I'll just write this down first, a squared x squared minus c squared x squared plus, now we have that, this part's all gone, so now we have this a squared y squared equals to now this a squared times a squared minus a squared times c squared like that. And then now we can do that some factoring. So factor that out. So we have a squared minus c squared, and then we factor out the x squared like that, and then plus this a squared y squared equals to, now we factor out the a squared, put that in front because it's just a constant, and now we have this a squared minus this c squared like that, which is quite interesting. Now this could be viewed as our preliminary form of the ellipse, and also want to make a note right here. Note that 2a, which was the distance of the 2 points, this is greater than 2c, and you could see that from here. C, 2c is going to be, well, from here to here is 2c, and then you have 2a is the full length across there, so it has to be greater than it, and I'll just draw that part out like this, just for reference here. So if we have a parabola, an ellipse like this, where this is the two foci, the distance here is 2c because that's c and c, and this one obviously has to be bigger, and that is our 2a across. So this and this sum up to 2a. So 2a is greater than 2c, so then what we have is, well, cancel the 2, a is greater than c, and thus what we end up having is this a squared minus c squared is going to be greater than 0 because a squared is going to be bigger than a squared is going to be bigger than c squared because a is bigger than c. So we have that. So those are positive like that. So yeah, now for convenience, what I'm going to do is, well, try to simplify this a squared minus c squared and let basically b squared, a new value, new constant b squared, equals to a squared minus c squared like that here. And also, good thing about this is I'll write also, if we rearrange this, move the c on the other side, we get a b squared plus c squared equals to a squared like that, which will become pretty handy later on as I graph the ellipse, because then we get a right angle triangle according to a Pythagorean theorem like that, that is in this form like that, where the hypotenuse is a squared. Yeah, so now then the equation of the ellipse becomes, because replacing that with b squared, we get now b squared x squared plus a squared y squared plus a squared y squared equals to a squared, and then that's going to be b squared like that. So that's why we change that to b squared, because it's easier to write. And notice what we have here, we could divide everything by b squared, so I'll just divide both sides by a squared, a squared b squared, like that. Divide this by a squared b squared, and then what we end up getting is, on this side the b squareds cancel, we're left with x squared a squared, and on this one we have the a squareds canceling, we'll have y squared over b squared, and this side both sides cancel, we have 1. And there's our equation of an ellipse. And yeah, that's the common ellipse formula. And now what I'm going to do is, well, note the difference between a and b in this case is, note, since we let b squared equals to a squared minus c squared, so this means that you're subtracting from a squared. This means that this is, well, obviously going to be less than a squared. Yeah, so what we have is a b squared is less than a squared. In other words, you can cancel that out. This just means b is less than a in this case. So then we have, here, b is less than a. And that's the difference between here, and we get an ellipse that is that horizontal flat one. Yeah, if it was greater than it, I believe you'll get that vertical ellipse. We'll get to that in a bit. And now we could find the x-intercepts, that's on the x-axis, those points, by setting y equals to 0. So what we get is, well, x squared over a squared is going to be, plus, well, y squared is 0 equals to 1. So we could rearrange this. We'll have x squared and then move that a squared on the other side equals to a squared. So in other words, square these, and then we get x equals to plus or minus a, like that. That's going to be the vertices, or the x-intercept. And the corresponding points, a0 and negative a0 are called the vertices of the ellipse. And the line segment joining the vertices is called the major axis. And now to find the y-intercepts, we set x equals to 0, so these are going to be on the y-axis. So when we do that, well, this part goes to 0, 0 plus y squared over, now it's b squared equals to 1. Rearrange this, we get y squared equals to b squared. In other words, square both sides. Y equals to plus or minus b, like that. And now another note, the ellipse formula is unchanged when we replace x with negative x or y with negative y, so the ellipse is symmetric about both axes. And you could see that basically if you put a negative x squared, a squared, plus negative y squared, b squared. Well, these are just the exact same thing, that it's going to be positive regardless because of the squared. So we just get x squared plus y squared, like that, over a squared over b squared. This equals to 1, etc. Also notice that if the foci coincide, if it means f1 is basically the exact same point as f2. If we get this situation, then basically c, the distance from to the origin is going to be 0. And I'll show you that in a bit. So that a equals b and the ellipse becomes a circle with radius equals r equals a and b equals to r equals a equals to b. And you can see this, that the c is going to be 0 because it's, well, together. If these coincide, these just have to go into the center and the origin over there, so c is 0. So this is when we get a circle. So if c is equal to 0, then what we have is, well, b squared by definition, what we let is equal to a squared minus c squared. That goes to 0, so we get, well, a squared minus 0 equals to a squared. In other words, b equals to a, and we'll write r equals to a equals to b, like. Or other way around, b, just because it's order, b equals a, and then we just let that equal to r, like that as a radius, like this. So then, thus our ellipse formula becomes x squared over a squared plus y squared over b squared. This equals to 1, which equals to, now we just replace those, x squared over r squared plus y squared over r squared. And now we can multiply by r on both sides, so then these cancel and we get r on the other side. So we get x squared plus y squared equals to r squared, the radius squared, like that. And this is the circle we're used to. And if you were to draw this quickly, this is just a circle. This is an ellipse that looks like a circle. So then you'll have this circle like that. At this point here, this is our f1 equals to, I'll write this better as f1 negative c0. This equals to f2 at c0. And if they're equal to each other, well, the c's have to be equal to 0. So that just equals to, call that f0, 0, like that. And then the vertices are going to be at this point where r is equal to a. That's just going to be r0, like that. And again, this is just r, the radius, and at this point is going to be 0r, etc. This one's going to be a negative r0, and then this is the vertical one over here. This is a 0, negative r, and again we get a circle like that. Circle there, and this formula is that. And now we can basically summarize this whole section or this whole video on ellipses as follows. An ellipse is, in this case, so if we have an ellipse, the formula is going to be x squared over a squared plus y squared over b squared, like that. this equals to 1. There's the formula. And in this one we have a is greater than or equal to b, and this is all greater than 0. If it's equal, we get a circle, etc. And the foci are going to be at plus or minus c and 0, where c is just equal to where c is equal to a squared minus b squared. And again, this is just in a bubble rearranging the definition of b, where we let b squared equals to a squared minus c squared. So if you move this over to this side and move the b onto the other side, that is what our c is equal to, because we're written a and b like that. And now that's the foci, and then the vertices are gonna be at, and yeah, these vertices are gonna be on the major axis, and this is gonna be at plus or minus a 0, where a is bigger than b. And then if we were to graph this out, what we end up getting is something looks like this. This is the x, this is the y. So we have over here, these are the foci. So this one's at negative c 0. Then we have here is at c 0, like that. Then what we have is the vertices. This is are at a and 0, and this is at negative a 0. Move that over here, so we're going to draw it soon, like that. Then the y-intercepts are going to be somewhere across here, and I'll write this as this point is going to be 0 and b, and then the bottom one's going to be somewhere over here. That's at 0 and negative b, like that. Then if we were to draw this all about it, we get a shape that looks something like this, and there's our ellipse like that, which is pretty cool. I'm surprised that my drawing was much better than usually at first try. So now that we have this distance, again, that's b, this distance from here to here is c, and like I showed before, these are related such that a is the biggest one across here, a squared is equal to, well, just by Pythagoras, b squared plus c squared, like that. And also by definition here, you can just rearrange that as I showed above, which is the cool part about defining b like that. So you can just move the c on the other side. So that is a very cool part of it, like that. And this is the origin, this right angle. You have a all intertwined together like that. And again, the major axis is on the a side, which is larger, so that is the major axis, like that. And I'll write, the a part, these are just the vertices. Vertice 1, this is vertice as well, vertice, like that. And now similarly, if the foci of an ellipse are located on the y-axis instead of the x-axis, so at 0 and plus or minus c, then we find its equation by interchanging x and y. So we can interchange that. So what we'll have is now y squared over a squared plus x squared over b squared, like that. Like that. So now we have x is over the b and y is over the a. This equals to 1. So when we put this all together, I'll just write this in a summary format similar to above. So we get an ellipse that we have, and write this in, usually you have x squared over b squared first, and then y squared over a squared, so move that on the other side, equals to 1. So there is our ellipse, where again we have a is just greater than or equal to b, and this is greater than 0. So again, a is going to be the major axis, a is greater than b, but now it's under the y as opposed to the x, so that's going to be on the vertical axis. And then the foci is going to be, so if we switch them, we had 0 and plus or minus c, and the vertices right here are going to be now at 0 and plus or minus a, so it's on the y-axis. And again, where here we have where c squared is just going to be a squared minus b squared. a squared minus b squared, like that. And then if you were to graph this out, we get something that looks like this. This is the x, this is the y, and then we get a curve that looks like this across there, where this is the foci across here. This is at 0, c, and this is at 0, negative c, and then at this point is the vertices. We have 0, a, and this part is 0, negative a. Now we have on the x-intercept 0, not 0, we have b, 0, and now we have here negative b, 0, and now the a, or the a value, this is going to be b now, this is c, and now we have our a there. We have again a squared equals b squared plus c squared, and now this is the major axis on this case, major axis, like that, and there is our vertice, like that, and now this is our vertice on this part, like that. And yeah, there's the origin. So yeah, that is pretty much it. That's all for today. Hopefully you followed through this pretty extensive definition, but I wanted to go over it in a lot of detail. So you watch this, you pretty much know ellipses inside and out. And obviously you can shift them by adding, let's say if you had over here x, you could add x plus whatever, x plus 2, and then it will shift it across, or y minus 3, etc. It will shift where the ellipse is placed. Anyway, that's all for today. If you learn also this brief history lesson on Johannes Kepler, and stay tuned for another video. Anyways, like always, you can download these exact notes in the link below, as well as viewing these in article format on Steemit. So anyways, thanks for watching, and stay tuned for another math easy solution.